Hello, pre-calculus honor students. Here we are with parabolas in 6.5. And let's start off with the geometric definition of a parabola. The set of all points equidistant between a point, focus, and a line directrix. So the book puts this at the end because it's much different than the hyperbola, the circle, and the ellipse. Because you don't have two foci, or even two foci coming into one to form the center of a circle. You only have one focus, and you actually use a line called the directrix. So let's look at this dynamically in GeoGebra. And you can do this too, and I encourage you to, is go to, under the conic sections thing, the parabola grapher there, and you can create your own parabolas just by putting down a point. You actually have to have a line too. You have to have a directrix ready to go, so I usually make those ahead of time, and that's what I did here. So you can see as I move the focus around, things change, because the point is staying in between the focus and the line. But not just that, it is staying equidistant between the two, and that's why I'm measuring over here in the purple point P. Notice the distances down here, staying at 2.89 and 2.89, and this is the difference from P to C. Unfortunately, this is called C, is the point I put up here before, and I changed its name to focus. And P little a is this line, y equals 1. Now, the distance from a point to a line, I actually give a formula for that in the review pack. If you start doing things like this, hello, and notice how you can change the direction of the parabola. You can get it to be a vertical parabola, or a sideways parabola by having a vertical directrix. You can have it pitched like that. And usually notice when you do that pitching, you create this XY term. If we take them back down to here again, you get that. You don't get an XY term. And that's mostly what we're going to study in this chapter, is horizontal and vertical parabolas. Now, some of the points we like to plot too are this vertex, which happens halfway between the focus and the directrix, and also these endpoints of the focal width. And notice how you take this distance here of 2 and exactly double it in each direction. So we're going to call this gap here P from the focus to the vertex. And then you go 2P each way perpendicular to that to come up with a couple more key points. So it's these 3 points I'm going to want you to plot on any parabola in future. Let's repeat this in our notes. So here we go. The set of all points equidistant between a point, focus, and a line, the directrix. And let me put in some little notes in here too. Some of the ideas: there's only one axis of symmetry, and that comes right down the middle here of the parabola. There's the axis of symmetry. And then we're going to abbreviate that from now on as AOS. There's no center to the parabola. We do have the vertex. And we're going to use HK to represent the coordinates of the vertex in all our formulas. And it's the point of closest approach. And then P is this gap. This gap like this. This is P and this is P. And we go 2P each way, perpendicular to the axis of symmetry, to come up with the endpoints of the focal width. So that gives you a nice idea of the shape of the parabola and how it sets about the focus. Because notice 2P each way, because when I'm over here, I'm going to be 2P away from the line and 2P away from the point, the focus. All right. Now, before we get into these things, I want to show you what we've got in the formula sheet. Notice the main difference with parabolas is that only one of the two variables is squared. Also, we don't have the A, B, and C coefficients we saw before in the ellipses and hyperbolas. Instead, we just use this idea of P, the gap. And P can be positive or negative, and the absolute value of it represents the distance from the vertex to the focus, which equals the distance from the vertex to the directrix. There's formulas here for the directrix and focus and vertex and all this, but what you should get is the idea down of how did I come up with these endpoints of the focal width and so forth. Notice in each case here, you go 2P each way from the for the focal width from the focus. See this? Focus at h comma k plus b, so h plus or minus 2p. That gives you the overall focal width of 4p. And later on I'll tell you why the eccentricity of the parabola is exactly 1. Whereas the hyperbolas, it was greater than 1, and ellipses was between 0 and 1, and a circle, the eccentricity is 0. Because it's one of these special borderline conic sections. So let's try our first problem using these formulas. Y equals 2x squared. Find the focus and the directrix of each parabola with its equations given. And I also want to get this onto a graph. Well, we see nothing subtracted from x or from y, so we can look at this as y minus 0 equals 2 times x minus 0 squared. And a lot of you might say, well, why do I need all this? I know what this looks like. It goes through 0, 0, 1, 2, 2 goes way up to 8. And that's how we used to graph parabolas. But now I'm going to be interested in a key point here, and that is where's the focus, where's the directrix? And a lot of kids mistakenly just put it here at 0, 1. Oh, no, 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 no. See, a half only goes to a fourth. No, a half squared is, a half does go to a half right there. Okay. Now, what I like is putting the 4p on the coefficient over here. So I actually would write it as 1/2 y minus 0 equals x minus 0 squared. And so 4p equals a half. So p equals an eighth. So that tells me that the vertex here at 0, 0 is going to be an eighth away from the focus and an eighth away from the directrix. Well, there's clearly a happy parabola, a vertical parabola going up, and you wrap around the focus, so the focus is going to be a here at 0 plus an eighth. And the directrix is going to be a horizontal line way down here at 0 comma, y equals negative an eighth, equation of a horizontal line. Now, our next problem, we have x equals 1/20th y squared. I prefer to write it as 20x equals y squared. And so we have 4 times 5 times x equals y minus 0 squared. I suppose I could put the x minus 0 in here as well. So we can emphasize that the vertex is at 0, 0. 4p equals 20, so basically p equals 5. That's why I wrote it as 4 times 5. And so now this time we have a lot more play here. It's not so cramped in. But because the y is being squared, y is squared instead of x, that makes it a horizontal parabola. So from the vertex, we're going to expect the focus to be to the right of the vertex. So we go 5 to the right, 1, 2, 3, 4, 5. And there's our focus. And the directrix will be 5 behind it, 1, 2, 3, 4, 5. So here's the directrix out here. And now to get a decent graph, we should really go 2p each way. So we came up with a focus so far of 5, 0 and a directrix of x equals negative 5. And this one's going off to the right because of the positive coefficient. Now let's get some more points on here. And that's 2p each way. So we're going to go 2 times 5, or 10 each way from the focus. So up 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just fitting onto our graph paper here. And that should be enough for a nice graph. You can also check, if this is the point 5, 10, and this is the point 5, negative 10, you can make sure both those work in the original equation. And they do, because when you put in 10 or negative 10, you square 100 squared divided by 20 is 5, so x equals 5. Okay? Now, this one gets a little trickier. Find the equation given information about the parabola. For the vertex at 0, 0 and a directrix of x equals 2. So the vertex is at 0, 0 and a directrix of x equals 2. That's this. Here, let's try a better horizontal line than this. There we go. There's our directrix. So what we come up with right away is that you're always going to be going away from the directrix. Think of it as a big box fan, and it's blowing it to the left this way. So the vertex is going to start here, and so the focus must be the left here. So the first thing we determine is our gap P equals 2, because the vertex is 2 away from the directrix. So that means we have to go another 2 to the left to come up with the focus. So that puts the focus at -2, 0. And the endpoints of the focal width, so 2p each way, so we go 4 each way, 1, 2, 3, 4. Notice how this point now is 4 away from the focus and 4 away from the directrix. Same thing with the point up here. So we get the endpoints of the focal width. Endpoints of the focal width at -2, 4, and -2, -4. So there we go. That's our rough sketch of the parabola. Now the equation, for the equation, we know the standard form since it is horizontal, and I know that because of the orientation of the directrix. If the directrix is vertical, the axis of symmetry will be perpendicular to our horizontal, making a horizontal ellipse. And a horizontal ellipse, it's 4p times x minus h squared equals y minus k squared. And I put one too many squares in there. 4p times x minus h equals y minus k squared. Well, our gap p is 2, but notice I'm going to put -2 in there because this is going to the left. Times x minus h, now we need the vertex at 0, and y minus 0 squared. So when we simplify, -8x equals y squared for our equation. And we can try our 2 points in there, -2, 4. -2 for x, you get 16, 4 squared is 16, -2, -4, that also works. There you go. Now let's try a homework problem. And if you're confident, you go start at this point. Otherwise, you can watch as we do a few more of these, and I'm going to do some GeoGebra backup on these as well. The coordinates of f of an equation of the line are, the coordinates f, that's the focus is given and the line. So the focus is at 0, 2, and the line is y equals -2. So here's 0, 2, and you have the line y equals -2. And so write and simplify an equation that expresses the set of points that are equidistant from f and d. So yes, we could do our typical trick here to come up with the equation, but I want you to see where the equations come from in terms of the coordinate geometry of it. So let's look at the typical point xy here. And this is f, and this is the directrix d. So the distance from xy to f must equal the distance from xy to line D. Now the first one's not too bad because we've got our hold it. Because, and let's just hang on for a second here. I'm trying to shift things around here just so I can write on the page correctly. Here we go. This is the distance from xy to f, which we said was 0, 2. And that we could put in the distance form, the square root of x minus 0 squared plus y minus 2 squared. Now the distance from xy to d, we have to think of the point. The point, so we've only taken care of so far, is this distance like this from f to xy. Now we have to think of this distance coming straight down like this. Well, think of the point directly below it. You'll have the same x-coordinate, but its y-coordinate will be the y-coordinate of the directrix. It's the directrix y equals -2. So all points on this horizontal line have a y-coordinate -2. And the distance between these two then is just y minus -2 for that distance from the lines there. Now we can go ahead and, before we get back to the formula, we can pin this down and open up some space and work on squaring this out. So when we square both sides, we'll get x squared plus y minus 2 squared equals y plus 2 hold it. The distance from xy to x negative 2, that's definitely y minus 2, that's y plus 2. Well, that's where we're squaring both sides. So you get x squared plus y squared minus 4y plus 4 equals y squared plus 4y plus 4. Notice how the y squareds cancel out, which is what we expected in the parabola. Right? The 4's cancel as well. And we get simply x squared x squared equals 8y. Now, is that consistent with what we had on our graph? X squared equals 8y. Do the points work in here? And now we've lost our graph. Excuse me. And here's the graph. We've got definitely a point here at 4 comma, let's check, with 4 comma 2, 16, yep, and negative 4 comma 2, yep, they both check out. Lastly, let's find the vertex, focus, and directrix of this parabola, graph the equation, and check it with a graphing calculator or GeoGebra. So, we've got the x's being squared. So with the x being squared, we can conclude right away that it's going to be a vertical parabola. And we want to get into the form 4p times y minus k equals x minus h squared. So we want to complete the square on the x's. Well, let's actually move the 8 over here. Negative 8y minus 1 equals x squared minus 6x plus blank, and complete the square in the one variable here. Well, take half the coefficient on x is negative 6, that's negative 3 squared, that's 9, so we're going to add 9 to both sides. So we end up with negative 8y plus 8 equals x minus 3 quantity squared. And so when we factor out a negative 8, we get y minus 1 equals x minus 3 squared. We're ready for the vertex. 3, 1. You can plot that. 3, 1 is the vertex. We're also ready for 4p equals negative 8. So p equals negative 2. So it's vertical, but it's going to be going down instead of up because of the negative coefficient on here. So the focus is going to be below right here. Focus at 3, negative 2. Here was our vertex at 3, 1. And the directrix will be 2 above it. Let's use this. The directrix right there. And then go 2p each way from the focus. And there's 3 nice points then to plot. And we've got our graph, and we've got the equation. We got the vertex, and the focus we said was at 3, negative 2, and the equation of the directrix. Directrix is y equals 3. Okay, now we can check that with GeoGebra. Let's see how it looks. GeoGebra, not that one. It's the other GeoGebra apparently. Yeah, this one, yeah, definitely. Sure, if that's what we expected. Now I did a little something extra on here because I wanted to show you one of the advantages of a parabola, and that's how we can make parabolic mirrors. If you notice on here, if I grab this point, what I had the calculator do is draw the tangent line to the parabola at that point. The tangent line. That's this line going through point B here like this. And then what I wanted to do was come up with, imagine light rays coming into this parabolic mirror. That's these vertical lines right here. They're going to bounce off the mirror. Now, to determine how you bounce off a curve, you get the tangent line of the curve, and then you do a typical pool bounce. This angle of incidence equals angle of reflection. So I measured this angle of incidence here, and I turned the line that much to get a nice bouncing out of here. Now watch what happens as the light rays hit the different points on the parabola. Do you sense what's happening? The ones closer into the focus here are bouncing further, and notice the ones right at the back wall at the vertex are going to bounce right back toward the sun. But there's something common to all these lines, and I just came up with something that's a really neat trick, and it's under properties. I have to grab the line itself. There, grab the line. Now go to Object Properties, Show Trace, and here we go. Oh yeah, second time's a charm. And we can see all those lines, all that light comes down, down, and reflects into, what do we call this point? At 3, -1? The focus. Okay? Flange out.